Thank you very much, and thank you again. I think we're all having a great conference, very interesting talks, so excellent. I want to start out with some inspiration about why I'm interested in this. Then I'll talk about rope length and bring in the ideas from yesterday and talk about rope length. And I'll talk about another geometric idea, distortion, and then I'll talk about things that are happening right now in people's research. So this is sort of an overview talk because I'm not sure that people will know about this. Maybe you do. So it's a bit of fun. So we've just had the Olympics. So yeah, I was very happy to see this tower. Knot theory is everywhere. And driving past the Museum of Science, there's the Möbius band. That made me very happy. So these things are inspiring. And then I don't know if you know about the hagfish. Do you know about the hagfish? I learnt about this from Eric Rawdon recently. Well, it's a great example. The hagfish ties itself in knots and produces slime to get away. So we'll see if this link works. It's a hagfish, and here it goes. Oh! I'll do that again. This slime is being produced too. It's slippery, and then ping! So very, very interesting. So of course there's DNA and molecules that exhibit knotting, and I think I have a better picture. So this shows Gelphoresis. So when you look at DNA molecules, when they're knotted, you can ask yourself, how are they knotted? And when molecules are tight, they and short, they don't travel very far down the gel. And so you can look at these layers under the electron microscope and you see these knots. So something like this will come from this blob of DNA running through the gel. So somehow knots and molecules, knots and proteins, it's all very inspiring. I don't know this work because I'm not a biologist, but this inspires my mathematics. So let me escape out of that. Go back to the talk. And yesterday I talked a little bit about total curvature of knots, and just a reminder, it's the total angle through which your tangent vector turns. And we talked about the Ferry-Milnor, that the total curvature is at least 4 pi. And Milnor actually proved, Ferry was 1950, he proved an interesting result. He proved that the total curvature of a knot is at least 2 pi times the bridge number. You know what the bridge number is? It's the minimum number of maxima in a direction. And he didn't call it bridge number. Bridge number was invented by Shore in 1954. He called it the crookedness of a knot. So if you read his paper, it's interesting. Anyway, he showed that the bridge number is at least 2 for non-trivial knots. He also did some analysis. I talked about finite total curvature knots, carves. These are carves whose left and right tangent vectors exist everywhere, and you sum up the total curvature and it's finite. So they can have smooth bits and corners and cusps, but the total curvature has to be finite. So this is a very inspiring result for me, very inspiring, because, and I think maybe it's the first geometric result. definitely unsure, but it's a very new, it was the beginning of a beautiful story. And it relates the geometry of the knot, the total curvature, to something about the knot type, the knot invariant. And it's subtle, and it's tricky, and there's also some analysis in here as well. So there's geometry and topology and analysis, and this characterizes this area of mathematics. So what I might do is describe the rope length problem. And the idea is to minimize the rope length, so the length of a knot or link which has a tube of fixed diameter around it. I'll do the mathematics on the next page. This is intuition. And we'll call tight knots or tight links are those which minimize rope length for that knot type. So this looks like a chain that you wear around your neck if you're a girl, and it looks tight. Yeah, you can't make that any tighter, the length any more minimal. So the question is, what do tight knots look like? What shape do they have? And what's the rope length? Very basic questions. And in fact, the beginning of knot theory, these questions motivated the study of knot theory. If you read Lord Kelvin's paper starting out knot theory, he looks at the model of the atom was related to tight knots rather than to electrons and things like this. They had a different model. So people were interested in knots. So many, many years later, we come back to this question of rope length. So more formally, we're going to define the rope length of the knot as the quotient of its length over its thickness. And the thickness is the diameter of a largest embedded normal tube around the knot. So this is meant to, oh, by the way, diameter, some papers have radius. Some papers have radius, some papers have diameter. So when you look at the rope length, sometimes you have to multiply by 2 or divide by 2, depending on which choice authors have made. You divide the length by the thickness so that the rope length is not affected by scaling. If you increase the knot or shrink the knot to scale up and down, you'll get the same number. So this is meant to represent a knot, and this is meant to be a tube around the knot. And when I look at this picture, I think of one tube and another tube going around it. So that's what this picture is meant to capture. And this is a tricky definition, the largest embedded normal tube. What might affect that tube is the local curvature, how much bending your knot has. If I have bending, this tube can't get too fat because it'll intersect itself if it blows up. So the local curvature, so local condition, affects the thickness. And then there's a global condition, right? If my strands are close, my thickness can't increase because they'll bash into each other, they'll intersect. So this doubly self-critical distance, this is capturing this quality. So there's many people, if you look at the literature, many people have worked on the definition. There are many equivalent definitions. Oscar and Gonzalez and Maddox, Litherland, John Simon, Greg Buck, John Sullivan, Jason Cantarella, like there's many, Rob Kussner, many authors have worked on this definition. This is a choice of many equivalent definitions I've just made. So that's the definition. And so a basic question is, given a knot with thickness, can you minimize rope length in that knot type? It's a very basic question, and the answer is yes. Sorry, CKS is Cantarella, Kussner, and Sullivan. Cantarella, Kussner, and Sullivan. Jason Cantarella I work with, and John Sullivan was my PhD advisor, so I forget to write out their names in talks because I know them, you know. Sorry about this. So minimizers exist, and it's a certain smoothness type. It's C11. So C1 is the first derivative is continuous. The C11 means that the first derivative is Lipschitz. This is some analysis. So Lipschitz means the second derivative exists almost everywhere and is bounded. Okay, so if the second derivative is bounded, of course you have bounded curvature. Just think about that multivariable calculus, right, that you teach your students. So this was a very important result when it came out. And this paper is an Invenzione, so it's a really great paper. So in this paper, they described a family of tight links, and these pictures I've shown you are members of this family of tight links. So each component is tight. C11, you can't, this is strict, this smoothness class. Because if I look at this component here, it's made up of an arc, half a circle here, half a circle here, and then a straight line here and a straight line here. So it's C1, it's nice tangent vectors, but the curvature, the second derivative jumps from this part to this part. So you need to have C11. It's not going to be C2 or something. It must be C11. So they in their paper, they describe examples like this of tight links. But there are many links for which the rope length is not known. And what I mean by a keychain is this is like a keychain with 1, 2, 3 keys. I'm imagining a loop with lots of keys going around. And if you have, their arguments fail when you have more than 7 keys. It's not obvious what to do, because in their arguments they minimize each component separately, and when you have a lot of keys on your keychain, you can't do this anymore in an obvious way. Interestingly enough is that the minimum rope length is still not known after all these years. So we have upper bounds and lower bounds, but the lower bounds have not yet met the simulations. So this is a very hard problem for the knot types. And numerical simulations have shown that the trefoil is the shortest with minimum rope length about this, or 32 point something if you're doing the other definition. So about this. So I have some movies to show you, which is a bit of fun. So Jason Cantarella is my co-author. Here he is, Jason Cantarella, and he, you can find these in this knot tightening movies link. And you'll see a bunch of pictures like this, and then when you click on them, you see something like this, and you hit play. Ooh. So he's written a program which does basically some kind of gradient descent, and he's using the curvature and the self-contact to get this to work. I do not understand the details of this program, but he's written papers about this that you can find on his webpage. And I have another one that I really like that I played before. This is 1027. And here we go. This is a long one. Jason Cantarella is not the only person who has done simulations. Oscar Gonzalez and Piotr Piransky and Andrei Stasiak have also done simulations to calculate minimal rope length. But I know Jason and I like these pictures, so I thought I'd show you. It's interesting here, you think it might be stuck, but then it keeps moving. So something Jason worries about when he's making these movies, he was telling me, is depending on your start position, maybe you'll end somewhere else. So he has some movies of like the trefoil, this will just keep going. So there's the trefoil like this, very symmetric, which will be minimal. And there's the trefoil, is that right? Like this. And if you tighten it this way, you can get stuck. And the length will be longer than if you tighten it this way. So for some of the high crossing knots, maybe you can do better. But for the low crossing knots, things seem to be fairly well established. Okay, so that's some fun. So, okay. So it's interesting, still don't know. So the interesting problem and the difficult problem, one of the big problems in this area is not only to find the rope length, but to relate rope length to the knot or lig type using topological invariance. And there's been a bit of an arms race, a bit of a war, a bit of mathematical excitement about relating the rope length to the crossing number, which I've called n. And this is the goal, to find constants and integers such and numbers such that the rope length has lower and upper bounds in terms of the crossing number. And you can find families of torus lengths for which this is true. And Jason Cantarella, I forget his name, Faber, and Chad Mulliken used arc index, which we've heard talks about, to show this bound. It's about the order of n squared, and the constant's about 1.6. At about the same time, Yuan and Diao again showed that the rope length is less than 3/2 power, but the constant is very big. And he did this is why I've written this up. Okay, so yesterday in No's talk, we learnt about knots on the cubic lattice, and we learnt about the stick number and the length, and this was the length of those knots. And so No has this nice result in terms of the length and crossing number squared, but the way that Yuan and his co-authors proved this result was to actually look at stick knots on the cubic lattice, and he proved this result and he used knot projections and Hamiltonian subgraphs. It's an interesting paper to read. So the other thing I should say is that cubic lattice knots have been helpful for doing modeling, and we also heard about Yuan and Diao's result about the trefoil only needs 6 sticks on the cubic lattice and has length 24. That was yesterday. We've heard that a couple of times, I think. And Yuan proved this in order to get a handle on the rope length problem. So you can approximate these, you can smooth out the corners and get an approximation to rope length using these cubic lattice knots. So Yuan's result that the rope length of a trefoil knot is at least 12 stood for many years and was an important result. So that's some context for those results. So I was going to say that No wins when the crossing number is very small, because 3/2 is not very big, right? So for crossing number 2, 3, 4, 5, this wins. But for crossing number 1,000,000, Yuan wins, right? These constants can be improved. Yuan and his co-authors never claimed they were very good, and he makes some suggestions at the end of the paper on how to improve this. So that's some interesting history, and they've kept on going. Okay, they've kept on going because there's this conjecture that the rope length of the knots is linear or less. So as you go to infinity, you should expect in a family of knots, the rope length should grow linearly or less. That's the big conjecture, and yeah, it's still open. So go to it. Go prove some results. Okay, and I have a long, it's sort of like this geometric stick index, it's somehow natural to relate it to crossing number. Something that motivates my research is to try and relate rope length to one of the polynomial invariants. Yes?
Is there any simulation results that that would be the basis for that?
Conjecture? All of everything so far. Nobody has found a family with superlinear growth. So everything we know seems to justify this. So it would be surprising, amazing, wow, if this...
There would be some estimation for the constants.
Yes, I haven't written them down because people are interested in the asymptotics as crossing number goes towards infinity. What happens to rope length as you go towards infinity? Does that make sense? I just put the constants down for a couple of them, but they're all different. It's a good question. Thank you. Okay. So what I wanted to do, so we're in sort of to the third part of the talk, is to bring back quadrisecants and essential secants and show how you can find something neat about rope length. So just to remind everybody, I think everybody was here yesterday. When we're looking at secant lines, we're looking at the number of times they intersect a knot. So a quadrisecant is an ordered tuple of points that intersects in at least 4 places. And there are different types of quadrisecants, alternating, flipped, and simple. And I proved that every non-trivial finite total curvature knot has at least one essential alternating quadrisecant, where I'll remind you of this in a minute. And I've said FTC because, of course, C11 is FTC. So that was the motivation for me extending the result, is to have these essential quadrisecants I could apply to the rope length problem. But I did something more general because that's, hey, I'm a mathematician, that's what we do. Okay, so when we're looking at the rope length problem, what we do is we assume the knot has unit thickness, and then the rope length is just the length of the core curve, the knot. And because we're a thick knot, we have extra geometry. So what this picture is meant to represent is when I think about the, I imagine I have a curve, and here is my point P, this is my knot. And if you think about it, I have this tube of radius 1/2, and so I know that this is from the other picture, right? I know that any other strand, if I think about this point P, has to stay outside a ball of radius 1, right? Because I'm on my knot and I have thickness, apart from this arc which goes through the ball, if I'm somewhere else, I have to stay at least 1/2 plus 1/2. I have to stay at least distance 1 away from this point if I'm another arc of the knot. It's just very straightforward. You know that these curves, the curvature is bounded. You know something about the local geometry. So this point P is meant to be this point P here. And this arc of the knot is meant to be this other arc of the knot somewhere outside and away from that point P. And what I've just done is I've just picked some points outside, and I've asked myself, what's the least length that, let me add some more stuff. Yeah, so the curvature is bounded above by 2. Given a point on my knot, this is the unit ball. The unit ball contains a single unknotted arc with length at most pi. So I'm talking about this strand of the knot here has length at most pi. And then other arcs of the knot stay outside this unit ball. And what I've just written down here is the least length of an arc from A to B outside this ball is just this expression. This is a unit disk. This is just trigonometry and circle geometry. So I've just said maybe the path goes up here, but the least length will be a straight line, a segment of the ball, and another straight line. So I just wrote an equation down. Okay, so given our quadrisecant, here's an alternating quadrisecant. I'm going to let segment AB have distance R, segment BC have distance S, and segment CD, D should be over here, that's a mistake. CD should be distance T. And I want to find the length of my knot in terms of R, S, and T. And I want to compute a derivative. So if I look at this point B, I know my arc of the knot has to go all the way around the outside of that. So here's the picture. It has to go all the way around the outside. So what I've done is I've just said, oh, what's the least length that this thing can be? It's a straight line past part of an arc. Then there's another arc of the circle and a straight line. So I've just said the length of AC has to be at least this. And the length of AD, well, I have to avoid both of these balls. So I go all the way around, there's a straight line segment, and then all the way back. And then the arc from B to D has a very similar expression, except it's Fs plus Ft. And now BC is essential, right? So I'll talk about that in a minute. Okay, so you can just find nice expressions for the lengths in terms of R, S, and T. I want to make the comment that we'll use these equations and minimize with respect to the variables. And you'll notice that I have, if you think about it, there'll be a corner at the point A because I'll have a straight line and then an arc, and here I'll have a straight line and then an arc. So the derivative won't be smooth here. So if one could be bothered, I never have been bothered, one could do even better bounds where you involve the derivative. Okay, so just a reminder of essential. So we looked at knotted theta graphs. And, you know, if I'm interested in arc AB being essential, I take this parallel curve with zero linking number, and this loop delta is not trivial in the fundamental group of the complement. So I say this arc is essential. And then if I look at this secant, I'm essential on both sides. So I say this secant is essential. I hope that was enough. Should I say that again? Okay. So, and yeah, just a reminder, when I'm looking at quadrisecants, I want the segments to be essential in the right places so that the quadrisecant will have distance. Okay, and then when you're an essential arc, you know that you have to, you know there's going to be this boundary intersection when you look at this arc. So you know this arc is going to have some length. And to cut the story short, you can you can work out the equation for the length depending on the distance between these 2 points. This is a unit ball, so the diameter is distance 2. So if my points A and B are far apart, well then I can go around the outside. If these guys are less than 2, then I'm going to have to go around the long way. So that gives us some length for the essential. So what we do is we put all these expressions together and we minimize, and we do it for all the different quadrisecants, and we get these numbers for alternating quadrisecants, essential simple and essential flipped. So we now know, this is my work with Yuanan, Diao, and John Sullivan, that a non-trivial knot has rope length at least 15.66. And to my knowledge, no one's done any better. No one's bothered to fix any of this or do any better. And another sort of something that motivates my research, because I'm interested in topology and geometry, is maybe I could find better bounds on the rope length using more than one quadrisecant. If I could relate the count of quadrisecants to polynomial invariants, perhaps I could relate rope length to polynomials invariants. So there's a whole research program in my mind to do with this problem in quadrisecants, and I don't know if it will work, but this is what motivates me in my mathematics. One of the problems which motivates me. Okay, so thought we'd change topics if we're okay, and talk about distortion. So there are many energies like rope length you can put on a knot. I haven't talked about Möbius energy at all. That's a topic of a different talk. I haven't actually done very much mathematics in this. But let me talk about distortion, which is a very sort of interesting and difficult thing to think about. So let's think about a tame knot. And let's pick 2 points on my knot and let this distance be the minimum arc length. So here we go. I can pick 2 points and I can go around this way or I can go around the other way. And I ask which are the smallest of these 2 distances, and that's what I'm calling dpq. And then I'm going to take the length of this chord and I'm going to take the quotient. So the distortion of those pair of points is this quotient. And of course, if your knot is at all smooth, as q approaches p, you have the curve to the chord, and you know, if it's smooth, of course this quotient will be 1. Sort of basic calculus, and the distortion of my curve is the supremal distortion between any pair of distinct points. And when the curve is smooth enough, supreme will be maximum when you're smooth enough. Okay, so lots of questions and there's some facts known. So this is Gromov who proved this. Given a closed curve, your distortion is at least pi over 2. So you should think pi around the top and 2 across the middle, with equality if and only if you're around planar round circle. You can relate distortion to rope length and show that the distortion is at least the rope length divided by 2. Lots of people did this. Sullivan and Kussner did this, and I think Greg Buck and John Simon proved this result too. I forgotten that second reference. And then if you have an arc of total curvature, so if you just have a part of the knot and you know something about its total curvature and it's not too bended, right? It's less than pi, you can show that it's at least distortion is at most this. Distortion has to be less than that. And that involves some integral geometry. It's nice. Distortion is very tricky. It's very tricky because of this supremal or maxima. It's very delicate and strange, and you think you understand it and then something goes wrong is all I can say. So Chad Mulligan, who was a doctoral student of Jason Cantarella, I think this should be 2007 is when this was published, found a trefoil with small distortion. But then what you can do is you can scale these trefoils and make them so you can have your trefoil and you can have your trefoil and then you can have your trefoil, right? If you scale the trefoils appropriately, you can build this infinite sum of trefoils which has small distortion. And this should horrify you, right? If you have an infinite sum of trefoils, you have infinite crossing number. You have infinite total curvature. You have infinite rope length. And finite distortion? What? right? So this is distortion is tricky. It's just what I'll say. It's easy to get confused by it. It's my experience. If you have a polygonal knot and you take the minimum of the distortion of all polygonal knots over a knot class and just compare it to the minimum over just any tame knot, like continuous embedding, not necessarily polygonal, are these two things equal? So remember, when you can have a very pathological embedding and you can suddenly shrink the distortion. So here is a round circle and you can put a little pimple in and the distortion goes right down. So this is an open question. Nobody knows it, but nobody knows very much about distortion at all. And yeah, do distortion minimizers exist, huh? So the most basic things aren't known. So those of you who know about distortion know the following very famous question by Gromov, which is, does every isotopy class of knots have a representative with distortion less than some finite number? He picked 100. Maybe a different number. And this has been plaguing mathematicians, some very, very, very smart people, including Andrew Casson, I happen to know, and some other people, very famous people, have worked on this and got stuck. And then John Pardon, the answer is no, and this is very new. John Pardon, who I think was an undergraduate at Princeton. Oh, it's okay, it's okay. He's now a PhD student, I believe, so it's okay. You know, Milner was an undergraduate when he produced his total curvature result. It's okay. There's plenty of mathematics for us all. It's okay. So anyway, this is a new result, and of course it's been published in the Annals. And you know, he shows that if you're a PQ torus knot, then the distortion is at least this, or a cabling is 160 isn't important. So his paper is worth reading. There's lots of interesting problems at the end. So my contribution together with John Sullivan was actually just the other piece of distortion that's currently known, is that if you're a non-trivial tame knot, then you have distortion at least this much. So we know distortion for unknots, right? It's pi/2, the minimal distortion. We don't know the distortion for any tame knot, but we know that like the trefoil is at least this. So that was a big improvement. And what we used was the fact that every non-trivial tame knot has the shortest essential arc. So when you look at, let me just improve this picture. If I pick this point A, and I look at this secant B, it's clearly inessential. This arc is inessential. And I can walk around, here is another B, I'm inessential. And then at some point, right, I become essential. And so in the middle somewhere is this shortest essential arc. And what you can prove is that if you're a shortest essential arc, and you're on the boundary of the set of essential secants, then you're in fact at least a trisecant, and these subsegments are both essential. So that, and then what you do is you do a lot of geometry and you prove a lot of things with inequalities, and then you get this number out. And the details are not interesting, but this is how you start the argument. So that was very fun writing that paper a while ago. So that's distortion. Lots of open questions with distortion. Very hard thing to understand. Okay, so I thought I'd say something about a different part of the rope length problem and describe a result by Jason Cantarella, Joe Fu, Rob Kustner, and John Sullivan. This is on the archive, and just before I flew to Korea, Jason told me it had been accepted by Geometry and Topology, but it hasn't been published, it's just been accepted, but you can find it on archive. So this is where the beginning of the talk I talked about topology, geometry, and analysis. So I wanted to say a little bit about the analysis. So you've seen the analysis come in when I've talked about the smoothness class of curves that you can talk about rope length for. And so what do you want to do? Is you want to do calculus, basically, is what you want to do. And you want to start with your knot. This is part of my knot. And I want to apply a vector field and perturb my knot and ask, how does thickness change? How does the length change as I perturb? So you want to do a derivative, and it's not just differentiating this curve because you have the constraints. You have the curvature constraints, and you have the right, this critical self-distance of your two arcs. So it's a constrained optimization problem. So your calculus students, you teach them Lagrange multipliers and life is good. This is much more subtle and difficult. So what these guys proved in a previous paper was something about Kuhn-Tucker theory, which is sort of, I'm lying, but it's sort of like an infinite dimensional Lagrange multiplier technique. I'm lying, but that gives you a flavor. It's very difficult. This balance criterion, this is this constrained optimization problem. This balance criterion means when you're a critical curve, when you differentiate with respect, you perturb your curve and you compute a derivative with respect to thickness, you want where the derivative is 0. And what comes into play is the local curvature constraint and these self-critical distances. And so they change the question. They give a useful criterion of when you can recognize curves which are in which are critical. And this is sort of like a lot of theory, and then in the second part of the paper they do examples. So they examine critical curves with no self-contact. So they don't think about this thing. They only consider curvature constraints. And basically they reclassify, they reprove some results, except they strengthen the results and show that you get supercoiled helices. So you're used to, if you've done enough differential geometry, which may or may not be the case, or if you've taught it, which may or may not be the case, right? You know a helix will be one of these critical curves, and then you can supercoil them and do some interesting things. So they look at, so they completely classify these curves, and they look at critical curves and parts, subsets of critical curves that don't have any of this self-critical, that just have the curvature constraint. And they show that they're parts, subsets of these supercoiled helices. So they're trying to get a handle on, from this balance criterion, they're trying to get a handle on what do we expect the curves to look like when they're in a critical position. And they do a very interesting and complete analysis of tight clasps. And tight clasps is you have one arc of the knot attached to the ceiling, one arc of the knot attached to the floor, so it looks like that. And it's really interesting what they do. So this is very, very exciting. It's a huge result, and it's difficult. It's very subtle. The analysis is really interesting. So now they've got a theory of like people have tried to do this for about 10 or 15 years. So it's very exciting. And of course, now they've got this. Once you get a first derivative, you want to know about a second derivative, right? So develop a theory of minimality, right? That's obviously the next big difficult thing to do. And I just want to make a remark that unlike rope length or Möbius energy or some of these other things, distortion is unlikely to have a criticality theory because you're dealing with a supremum, not with some kind of average thing. It's so you think to yourself, well, what do I want to do? I take my curve, I find the pair of points where I have maximal distortion. I perturb my curve. Doesn't mean these points will be there. Maybe they jump over here or over here. You don't know. So it's very subtle and difficult. And I spent some while, maybe 5 years ago, trying to do this and getting stuck. Chad Mulliken's PhD thesis, which has been published, he has a stab at this and is partially successful, but it's a very, very difficult question, and it's unlikely to be resolved just for theoretical reasons. Okay, so in the last 10 minutes, let me tell you a little bit about some work I'm doing and some of the other open problems. So this is this big set of open problems right here. And this balance criterion is difficult to work with too. Knowing what the structure of the set of struts is, this self-contact thing is very hard. They've answered the question, but I don't know how useful this is. So there's much more work to do to make this usable. So I've done, I found I wanted to prove my own criticality theory because there's nothing like proving something to understand it. So with John and Sullivan and Nancy Wrinkle, I started looking at immersed ribbons in the plane and wanting to minimize this ribbon length. And so this is work in progress, and immersed, we thought that 2 dimensions would be easier than 3 dimensions, and we were wrong. They're just, they're really interesting, but there are a lot of subtleties that come up with immersed curves in the plane that you don't expect. The main technical tool for the criticality of rope length was this Clark gradient, and we can't use those arguments here. So yeah, it's been an interesting project. And then I've done a related problem that was inspired by Lou Kaufman, which is to look at folded ribbons. Literally take a piece, like origami, take a piece of paper, squash it flat, and I've been doing this with my undergraduate students because it's very accessible. So they buy their ticker tape and they fold things and we prove things. And I really like this because there's some discrete geometry involved and also the mathematics of folding. Like, I'm really excited by this. So this was a nice project that I will keep doing with my undergraduates, understanding these folded ribbon knots. These students were at Smith. I'll work with students on Washington and Lee with this. So there's other things that you can prove. So back to sort of inspiring problems that are open. So I got these pictures of a protein molecule from Eric Rawdon. This is a big protein molecule with all the little proteins and bonds shown. It's a big mess, isn't it? It's huge. It's not like the trefoil knot. It's not something simple. And maybe you've seen pictures like this. So this is simplifying this picture, and it shows supercoiled parts where the proteins are supercoiled, and it shows the backbone structure. So maybe some of you have seen this. And then what you can do, what Eric has done, is he's simplified it even further down to a polygonal knot. Well, it's not a knot. It has open ends. So how do you model lung proteins mathematically? How do you do this? Proteins are open, right? They're open, they're not closed, they're not circular. So how do you talk about local knotting? The other thing about these protein structures is they may or may not be knotted here. You can have different looking proteins, physically different chemicals with different knotting, yet all the tangling means that they look the same as far as their behavior goes as of interacting with the DNA. So again, I'm saying this badly and I could be wrong in the way I'm saying this, but there's something to talk about mathematically with tangling. There's been a lot of work with knot theory or mathematical tangles and DNA. What about just all these strands all mixed up? How do you explain that mathematically? How do you talk about the structure? I don't even know how to start beginning to do this, but a lot of the mathematicians I go to conferences with talk about how do you model these things? How do you model local knotting? How do you model this complicated tangling? And along with this is how do you generate truly random long polygons? A lot of my colleagues do a lot of computer simulations. How do you think, oh, well maybe local knotting behaves like this. So I better construct, this is what my colleagues do, a lot of random polygons and run simulations and see if that works. So that, of course, depends on the fact that you can construct random long polygons. So there's a lot of interesting mathematics on the computational side, which is not understood. And do I want to say anything? I think that's all I do want to say. So again, I want to say thank you, and I have my wonderful co-authors and my students. And these three students did mathematics and economics, and they're now working. But these three students are now going to grad school, and they're starting in fall. So that's very exciting. And again, thank you so much for the invitation. I'm so happy to be here. So thank you.